All right, so now we're moving on to what would have been task 2 on the whiteboards if I had been there. You would be trying to do this with your team. And I wouldn't let you spend too much time on this because you would get stuck and go, huh? We can't use the tangent ratio because we don't know the opposite or the adjacent. So if we tried to set up the tangent ratio, tangent of 30 is equal to the opposite over the adjacent, but here's the opposite and here's the adjacent, and I don't have numbers here. So that would be two things I don't know, and I can't solve that. I can't use the Pythagorean theorem because if I was trying to use the Pythagorean theorem, this would be A and this would be B. And so I would have A squared plus B squared is equal to the hypotenuse squared. Again, I don't have numbers for either one of these. I can't solve a single equation if it has two missing numbers. I need to have only one missing number. So this leads us to the third thing we reviewed, which is similar triangles. Now, if I just had another triangle with a 30-degree angle with all the sides worked out, then I could use the scale factor. I could figure out the scale factor and use that to help me out. Well, the fact that there is another 30-degree triangle that exists somewhere in the world where all the sides have already been measured sounds kind of familiar. This is like when we first discovered the tangent ratio. The tangent ratio also worked on having two triangles that were similar, one where we knew all the sides, and then we could find the ratio of these two sides and compare it to the unknown sides that I have. So that's what we need to do. We need to come up with another tool like the tangent ratio. And sure enough, people have been really smart and they figured out that if you have two similar triangles, so like we did in the review, we have these two similar triangles, that if we divide the opposite by the adjacent, we're going to get the same answer, right? So we knew that. That's called the tangent ratio. We can just prove it. So if I do 10.19 divided by 20, I get 0.5, more or less. And then here, we had figured out the two missing sides here, 87.63 divided by 171.94. We also get 0.5. Okay, so the tangent ratio for a 27-degree angle is 0.5. The tangent ratio for this 27-degree angle is also 0.5. So I divided these two side lengths, I got 0.5. Divided those two side lengths, I got 0.25. And if I do the tangent of 27, it tells me also 0.5. So we knew that already, that the whole idea of the tangent ratio comes from similar triangles. If you have two right triangles with the same angle, they're going to have the same slope ratio. But what about if we divide other side lengths? What if we divide, say, the hypotenuse with the opposite side? So if I do that, if I do, say, 22.45, and I divide that by 10.19, from this one, I get 2.2. Okay, so keep that in mind, 2.2. When I divided this by this, I got 2.2. What if I do that here? 193 divided by 87.63. Aha, I also get 2.2. So the ratio of these two sides is the same as the ratio of these two sides. And I bet if I do the ratio of these two sides, it'll be the same as the ratio of these two sides. So we can check that out. So how about this time we do the adjacent side divided by the hypotenuse? What if I do 20 divided by the hypotenuse, 22.45? I get 0.89. And if I do it here, if I do 171.94 divided by 193, I get 0.89. Oh, same thing. Okay, so the ratio of two sides within a right triangle is going to be equal to the ratio of two sides in a similar right triangle. So it's not just the slope ratio that's going to be the same, it's the ratio of any two sides. So there are actually names for all of these different ratios. The ratio of the opposite over the hypotenuse, the ratio of the adjacent over the hypotenuse, the ratio of the hypotenuse divided by the opposite, the ratio of the hypotenuse divided by the adjacent. All of these have names. We, however, are going to start with just one of them. The one that we are going to talk about is where we're going to have the opposite over the hypotenuse. We're going to talk about this one. So here's my angle right here. The opposite side is the 10.19. That's my opposite. And here's my hypotenuse, is the 22.45. So this has a name, and I was going to have you figure it out what it's called in class by having you look at the calculator. So here's my big hint. It's one of the buttons in the calculator. So notice we've been using the tan button, and notice the two buttons that are right next to it. One that says COS and one that says SIN. So check this out. If I do the opposite and I divide it by the hypotenuse, so if I do 10.19 and I divide it by 22.45, I get 0.45. Okay, so 0.45. So let's keep that in mind. I got 0.45. So now, what if I try these buttons? Which one will also give me 0.45? So I know tangent of 27 probably will not give that to me because that is the ratio of this one over this one. See, that gave me 0.5. So why don't we try the next one, COS? So if I do COS of 27, that gives me 0.89. Nope, not what I'm looking for. Let's try the next one. So if I do SIN of 27, aha, there it is, 0.45. So which button was that we used? It was this one right here that has the letters SIN. It is not called sin. This is an abbreviation. Just like tan is an abbreviation for tangent, the SIN is an abbreviation for the word sine. So the word sine is spelled S-I-N-E. S-I-N-E is the name of the ratio. That is the opposite over the hypotenuse. So you could probably guess that the COS button is going to be the one that's the adjacent over the hypotenuse. So we can just check it out. If I do 20, here's my adjacent to the 27, adjacent to the 27. If I do 20 divided by 22.45, I get 0.89. And I think we saw that before, right? If I did the COS button of 27, I get 0.89. So the ratio of adjacent over hypotenuse is called cosine. See how it has the word sine in it, but it has a little CO in front of it. So these are all closely related. Sine and cosine and tangent, they're all related to how you make these ratios. Okay, and then I mentioned that you could also flip these, right? You could have hypotenuse over opposite. That is called the cosecant. And you can have the hypotenuse over the adjacent. That's called the secant. And you can have the adjacent over the hypotenuse. That's called the cotangent. So there's a total of 6 trigonometric ratios that mathematicians use, but we're introducing them one at a time. So we've been using the tangent ratio already, which is opposite over adjacent. And today I'm going to have you start using the sine ratio, which is opposite over hypotenuse. And so you're going to be doing some practice in Desmos. It's only going to ask you to use tangent or sine. However, I will put into MathSpace some practice with the cosine as well. So you're welcome to go ahead and work with the cosine as well. It's all of these problems, you solve them exactly the same way as we've been doing the tangent problems. So let's go back to this problem right here, where we have our 30-degree angle. And let's go ahead and use the sine ratio. So the sine of any angle, given a right triangle, is equal to the opposite side over the hypotenuse. This is our new ratio. So I can set this up because we're going to find the opposite and we know the hypotenuse. We know the hypotenuse. So I can say that the sine of 30 is equal to the opposite. Notice I had labeled that b before, so I'll go ahead and use b, over the hypotenuse, which is 15. And now I can take a table. I've left tables for you to use with the sub. So you can get your sine table. So you notice this one says SIN, which stands for sine. The sine of 30 degrees, let's find it on here, 30 degrees. Oh, it's exactly 5, or rather 0.5. So equals 0.5, 0, 0, 0. It's equal to b over 15. And just like we did with the tangent ratios, just put a 1 underneath it and use your cross multiplying. So I get b is equal to 0.5 times 15, which would be 7.5. Okay, we could also do that on the calculator. Instead of changing sine of 30 to a decimal, I could have said, well, I'm going to do 15 times the sine of 30. So 15 times sine of 30. And hit equals. And change that to a decimal, 7.5. So this side is 7.5. Now from here, I can figure out the other side. I could use the cosine ratio, or I could use the tangent ratio, because now I know the opposite and I need to know the adjacent, or I could use the Pythagorean theorem. So it's totally up to you how you want to do it. So let's go ahead and do Pythagorean theorem. A squared plus b squared, which is 7.5, has to be equal to the hypotenuse squared, the long side squared. So I can do 15 squared, I believe, is 225. And then 7.5 squared is equal to 56.25. So I need to minus my 56.25 from both sides. Let me just make sure I'm not having any problems with my brain today. Yeah, 15 squared is 225 minus the 56.25. And that gives me 168 is equal to a squared. So a is going to be equal to the square root of that. So I can do the square root of 168.75. And I get 12.99. Okay. A is equal to 12.99. Or like 13. Okay. So A is equal to 12.99. So let's say I wanted to do that, though, with the tangent ratio. So I already answered it. I found my missing sides. But, oh, and this would be, let's call this alpha. If I wanted to find my missing angle here, right? I could do 180 is equal to 30 plus 90 plus alpha. So subtract 90 from 180, I get 90. Then subtract 30 from that, and I get 60. So alpha is equal to 60. So this is 60 degrees. Okay, so I could also do my tangent ratio to find the adjacent. So I used the Pythagorean theorem, but let's go ahead and do it with the tangent ratio as well. I'm going to actually do it from here. So now that I know this is 60 degrees, side A is opposite and side B is adjacent. So I could do this. I could say tangent of 60, about to run off the edge of my table here. Tangent of 60 is equal to A over 7.5. And I can put that over 1, and I can do my cross multiplying. So A is equal to 7.5 times the tangent of 60. Notice I'm getting kind of fancy here. I'm not changing tangent of 60 to a decimal. I'm just writing it out so that I can put it in my calculator. So I have 7.5 times tangent of 60, and I get 12.99. Oh, exact same answer that I got when I did the Pythagorean theorem. So that's cool. Okay, so now we've got lots of tools in our toolkit. Boy, I just made a mess of this paper. Okay, so this is what we're going to be doing. We're introducing the sine ratio. So the sine ratio, sine is equal to the opposite of the angle over the hypotenuse. Okay, so whichever side is opposite over the hypotenuse. And so now you're going to be practicing that in Desmos. And if you want to throw in cosine, you're certainly welcome to as well. Okay. Notice I mentioned there were 6 trigonometric ratios, but you only see 3 of them here. You only see 3 of them here. The secant, cosecant, and cotangent aren't used all that often because they're just the reciprocal. They're just the reciprocal of cosine, sine, and tangent. So people generally just use sine, cosine, and tangent when they're finding missing parts of right triangles. All right, that's it. That's the new stuff. Go practice.